Welcome to the part 1 of our lecture 5 for the Thermodynamics course, and our topic for today is all about properties of pure substance. Defining a pure substance, it is a substance that has a fixed chemical composition throughout, meaning the mixture is homogeneous. The water, nitrogen, helium, and carbon dioxide, for example, are all pure substances. A pure substance does not have to be a single chemical element or compound, but a mixture of various chemical elements or compounds also qualifies as a pure substance as long as the mixture is homogeneous. Say for instance air. It is a mixture of several gases, but it is often considered to be a pure substance because it has a uniform chemical composition. However, a mixture of oil and water is not a pure substance, since oil is not soluble in water and it collects on top of the water, forming two chemically dissimilar regions. As for the figures below, this one, a mixture of two or more phases of a pure substance are still a pure substance as long as the chemical composition of all phases are the same, especially in this figure. And the mixture of liquid and gaseous water, and this is considered as a pure substance, but a mixture of liquid and gaseous air is not in this case. Okay? Since the composition of liquid air is different from the composition of gaseous air, and thus the mixture is no longer chemically homogeneous. This is due to different components in air condensing at different temperatures at a specified pressure. This is a typical example of a mixture of two or more phases that is a pure substance, because both phases have the same chemical composition, and this is a mixture of ice and liquid water. We all know that substances exist in different phases, and generally we have three phases: the solid, the liquid, and the gas. Defining a phase, it is identified as having a distinct molecular arrangement that is homogeneous throughout and separated from the others by easily identifiable boundary surfaces. When studying phases or phase changes in thermodynamics, one does not need to be concerned with the molecular structure and behavior of different phases. However, it is very helpful to have some understanding of the molecular phenomena involved in each phase. The intermolecular bonds are strongest in solids and weakest in gases. One reason is that molecules in solids are closely packed together, whereas in gases, they are separated by relatively large distances. While the molecular spacing in the liquid phase is not much different from that of the solid phase, except the molecules are no longer at fixed positions relative to each other, and they can rotate and translate freely. In a liquid, the intermolecular forces are weaker relative to solids, but still relatively strong compared with a gas. The distances between molecules generally experience a slight increase as a solid turns into liquid. In the gas phase, the molecules are far apart from each other, and a molecular order is non-existent. Gas molecules move about at random, continually colliding with each other and the walls of the container they are in, particularly at low densities. The intermolecular forces are very small, and collisions are the only mode of interaction between the molecules. Molecules in the gas phase are at a considerably higher energy level than they are in the liquid or solid phases. Therefore, the gas must release a large amount of its energy before it condenses or freezes. The phase change process of a pure substance depends on various conditions. At room temperature and pressure, copper is a solid, mercury is a liquid, and nitrogen is a gas. Under different conditions, each may appear in a different phase. Even though there are three principal phases, the solid, liquid, and the gas, a substance may have several phases within a principal phase, each with a different molecular structure. Carbon, for example, This is a carbon, and it may exist as graphite, as one-layer carbon, or diamond, a hexagonal structure carbon, meaning they have a different structures in the solid phase. While helium has 2 liquid phases, iron has 3 solid phases, and ice may exist at 7 different phases at high pressures. This is mercury, and this is the solid phase of the mercury, and this one is the liquid phase. This is a typical illustration of phase change process. We will consider an ideal frictionless piston cylinder device, and for state 1, we are contained with liquid water at 20 degrees Celsius and 1 atmospheric pressure. Under these conditions, water exists in the liquid phase, and it is called a compressed liquid or a subcooled liquid, meaning that is not about to vaporize. Heat is now transferred to the water until its temperature rises to, say, 40 degrees Celsius. And as the temperature rises, the liquid water expands slightly, and so its specific volume increases. To accommodate this expansion, the piston moves up slightly, and the pressure in the cylinder remains constant at 1 atmospheric pressure during this process, since it depends on the outside barometric pressure and the weight of the piston, both of which are constant. Water is still a compressed liquid at this state, since it has not started to vaporize. As more heat is transferred, the temperature keeps rising until it reaches 100 degrees Celsius, as shown in the second figure for the state 2. At this point, water is still a liquid, but any further heat addition would cause some of the liquid to vaporize. That is a phase change process from liquid to vapor. A liquid that is about to vaporize is called a saturated liquid. Therefore, in state 2, it is a saturated liquid state. Once boiling starts, the temperature stops rising until the liquid is completely vaporized. That is, the temperature remains constant during the entire phase change process if the pressure is held constant. And this can be easily verified by placing a thermometer into boiling pure water on top of a stove. At sea level, for 1 atmospheric pressure, the thermometer will always read 100 degrees Celsius if the pan is uncovered or covered with a light lid. During a boiling process, the only change we observe is a large increase in the volume and a steady decline in the liquid level as a result of a more liquid turning to vapor. This one is the vapor and this one is the liquid. Midway about the vaporization line, as shown in this state 3, the cylinder contains equal amounts of liquid and vapor. As we continue transferring heat, the vaporization process continues until the last drop of liquid is vaporized, this one, as shown in state 4. At this point, the entire cylinder is filled with vapor that is on the borderline of the liquid phase. Any heat loss from this vapor would cause some of the vapor to condense, meaning there is a phase change from vapor to liquid. A vapor that is about to condense is called a saturated vapor. Therefore, in state 4, it is a saturated vapor state. A substance between states 2 and 4 is referred to as a saturated liquid-vapor mixture, since the liquid and vapor phases coexist in equilibrium at these states. Once the phase change process is completed, we are back to single phase region. Again, this time, the vapor. And further transfer of heat results in an increase in both temperature and the specific volume. At state 5, the temperature of the vapor is let us say 300 degrees Celsius. And if we transfer some heat from the vapor, The temperature may drop somewhat but no condensation takes place as long as the temperature remains above 100 degrees Celsius for 1 atmospheric pressure. A vapor that is not about to condense is called a superheated vapor. Therefore, water at state 5 is a superheated vapor. Look at this TV diagram as I discuss the different heating process of water at constant pressure of 1 atmospheric pressure. This is an isobar, meaning this is at constant pressure. So we know that the saturation temperature is 100 degrees Celsius. And let's start at point 1 at 20 degrees Celsius. And since the temperature is less than the Tsat, we have a subcooled liquid here. If we add energy to our system, the temperature rises while the pressure remains constant. At point 2, with temperature at 100 degrees Celsius, where T here is equal to the Tsat. Therefore, this is a saturated liquid. As the fraction of the mass of water that is in vapor phase is 0, a quality of a saturated liquid is also 0. As we continue to add energy to the system, the first small bubble of vapor forms a system moves towards point 3. The quality increases from 0 but the temperature remains constant at Tsat. When a last small drop of liquid vaporizes, we reach point 4, saturated vapor. All of the water is in the vapor phase, so the quality is 1. Notice that the temperature is still at Tsat. When we add energy to the saturated vapor, the temperature begins to increase again, and the system moves towards state 5. Since the temperature is above Tsat at 1 atmospheric pressure, this is a superheated vapor. The quality is not defined in the superheated vapor. Let's elaborate more the phase change of water, and we will tackle the latent heat. Latent heat is the heat required for an object to change phase during melting, boiling, freezing, and evaporization and condensation. And this energy is closely related to enthalpy. In this figure, the ice has heat added to it. Adding heat to water can either raise the temperature or change phase. The temperature goes up, so that's the sensible heat. But once it starts melting, the heat is latent heat and is represented by the flat parts of the line during melting or evaporization. The latent heat of fusion is the heat required for an object to go from the solid state to the liquid state, or vice versa. Since its value is generally much higher than specific heat, it allows you to keep a cold beverage for much longer by adding ice than simply having a cold liquid to begin with. It's also why frozen meat takes a long time to thaw, and once it's thawed, it heats up quickly. Ice and water have enormous latent heats associated with them, which is why snow takes so long to melt and boiling water is used for cooking. The latent heat of vaporization is the thermal energy required for a liquid to vaporize to a gas, or the amount that is released when a gas condenses to a liquid. Water has a high latent heat of vaporization, which is why steam burns are so dangerous. When steam burns a person's arm, for example, this energy transfer causes the steam to condense, which uses much more energy than simply changing the temperature. Hot water would also burn. However, if a person were to get a hot water burn, that would only change the temperature of the person's hand and the water, and will not cause a phase change. Therefore, steam water burns are much worse because of a phase change that is actually happening. Thank you so much for listening, and we will continue our discussion to the next part of our lecture video, and we will discuss the following topics: the property diagrams for phase change process and the ideal gas equation of state. I will see you soon. Bye-bye.